So calculus students, here's the lesson 4 homework where we're doing derivatives of other trig functions. We have some table problems where we have more like notational derivatives. And then we have higher order derivatives, so like second derivatives, third derivatives, stuff like that. So you need to have memorized, this is one of the things to memorize, the derivatives of secant, cosecant, tangent, cotangent. It should be cotangent x. And I like starting off the first two problems like this because we just learned the product rule and the quotient rule, but I don't have to use the product rule for this. Like you might think it's a product, use the product rule, but we talked about how whenever it's a constant, a number, that you can just leave the number alone and then take the derivative of the function. Maybe put it in like parentheses if you want to. The derivative of secant is secant x tangent x, and you're good. If you were to use the product rule, you'd see there's just unnecessary work going in there. You'd have the derivative of 4, which is 0. That's the derivative of the first times the second, plus the derivative of the second. That's where the secant x tangent x comes from. Times the first. And you can see the 0 times the secant x, that goes away. So don't do the product rule if it's just a constant times things. Just leave the constant. It's the same here. Everybody might think, oh, you got to use the quotient rule because it's tan x divided by 8. But dividing by 8 just means we really just have a constant. You could rewrite this if you wanted to as 1/8 times tangent. Okay, very important. If you use the quotient rule, again, you just have a little bit of unnecessary work. You'd get the right answer if you use the quotient rule, but it's just not necessary. You could just leave the constant. Also, don't forget that this also means dy dx because I'm taking the derivative. That's just d dx. When you take the derivative of y, you can write it as y prime, or you can think about multiplying and you get dy dx. Leave the constant, multiply by the derivative of tangent, which is secant squared. Okay? And just to show you the quotient rule, you would have the derivative of the top times the bottom minus the derivative of the bottom times the top, which would go away because it's 0. All of the bottom squared. You would end up with 8 secant squared x over 8 squared, and then one of the 8's would cancel, and you'd end up with 1/8 secant squared x. So again, like, don't use the quotient rule, don't use the product rule, unless you have a product of functions with x's. Don't worry about it with constants like this. This is a constant. So I would rewrite this before taking the derivative as 1/4 cotangent x. And then I would take the derivative and I'd get 1/4. And the derivative of cotangent is negative cosecant squared x. You're multiplying these things together. If you wanted to rewrite it, it wouldn't be 1/4 minus. Some people make that mistake, but it'd be negative 1/4 times cosecant x. I'm just moving the negative over, just multiplying. Now, secant x times tangent x, this is a product. So we need to be prepared to use the product rule if you have x's times x's. Yeah? So here it is a first and a second. I would take the derivative of the first. That's the derivative of secant times tangent. And then I'd add the derivative of tangent. That's the derivative of the second times secant. Now, this is fine. Maybe for like multiple choice, you would need to be able to rewrite it. Secant squared times another secant will be secant cubed. And potentially you'd be ready to, for multiple choice, factor. Again, we factor so we can like solve things. Solving things are easier when we have products, so we can set it equal to 0 potentially. And that's what it'll be, okay? Down to this one again, 3 is not a function, it's just a constant. You could leave it alone. The derivative of cosecant is negative cosecant cotangent. If you wanted to rewrite this, you can move the negative in front of the 3. Make sure you know you're multiplying everything together, not adding or subtracting. This is a product. X over 3 times cosecant x. X over 3, I know, is just like 1/3 x. I would not use the quotient rule for x over 3. I would say the derivative of x over 3 is just 1/3. It's just a line with slopes of 1/3. So that's the derivative of the first times the second, plus the derivative of the second, negative cosecant cotangent, times the first. I'm going to write it as 1/3 x. If you'd like to, you could like factor out a 1/3 cosecant. You have 1 plus x cotan x. Again, not necessary if you're just plugging in numbers. If you're just plugging in numbers, you just plug in the number. But if you were to solve an equation or simplify for a multiple choice question, you could do that. I messed up. There's a negative here, so there should be a negative there, or 1 minus. Now, bringing in notation, when we get to our table problems, we're going to have to take derivatives of just like notations, like f's. So if I have x squared f of x, it's a product. I'm using the product rule. Derivative of x squared we know, but it's simple. You just got to do it. The derivative of f, you say, is f prime. It means the slopes of f. Okay? Maybe we factor out an x, y, because we can. Is it necessary? No. When we do our table problems, we won't need to factor. We can just plug in. This is a quotient of 2 functions with x's, so I would use the quotient rule. Derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. I could factor out an x from the top and cancel 1x. Not necessary if you're just plugging in numbers, but maybe this helps you plug in numbers a little bit easier. It's 1 less x to plug in. After factoring, you can cancel. All right, I'm asking you for a second derivative. So I want you to take the derivative and then the derivative of the derivative. You'll be able to find the slopes of your derivative, which will be useful in the future. The derivative of cosecant is negative cosecant cotangent. Okay, so I took a derivative of a function and I get this. But now I want y primes prime or y double prime. Okay, y primes prime, y prime slopes, we'll call y double prime. It's a product. Again, the negative could be left out as a constant, or you could just bake it in to the negative cosecant, and I'm going to do that. I have the derivative of cosecant, which is negative cosecant cotangent. The negative and the negative will cancel with each other, giving me positive cosecant x cotangent x. Again, that's the derivative of negative cosecant. So that's the derivative of the first times the second plus the derivative of the second, which is negative cosecant squared, times the first, which is negative cosecant. The negatives will cancel because you're multiplying 2 negatives together. That's a positive. If you'd like to factor out a cosecant, you can. I'd have two cotangents multiplied together. One of these cosecants is gone. Now, potentially, this is equal to something. If you remember, like sine squared plus cosine squared equals 1, it's kind of how we discovered the derivatives of sine and, of secant and cosecant and stuff like that. Which means let me divide by sine, and I get 1 plus cotangent squared equals 1 over sine is cosecant squared. Maybe I can use this identity to simplify this. I can't though, like cosecant minus cotangent is 1. I have cosecant plus cotangent, so like I wouldn't. But just like if you see something crazy, maybe in like another practice problem, maybe on the AP classroom problems, you see a simplification and you're like, what the heck just happened? They might have used a trig identity to simplify things, okay? Over here, let's find the second derivative. Again, that x cubed over 3. Yo, I'm not worrying about it. I'm not using the quotient rule. It's just a constant times a function. So I bring the 3 down times 1/3, and I just get x squared minus 8x plus 0. That's important. The derivative of 2 is 0. Don't forget about that, which means the derivative of the derivative is 2x minus 8. The second derivative is 2x minus 8. We know that since this is a whole number that's positive, we'd eventually go down to 0, like the derivatives of the derivatives of the derivatives. So some fun problems with these are like this notation in calculus means the 52nd derivative. And it's like, holy cow, 52 derivatives. Well, you don't have to worry about it if you notice. There's going to be a pattern that emerges. When I get to the fourth derivative, I'm going to get back to the start. You can use 3 tick marks, or you can start using the number 3. We usually don't go past 3 tick marks. And you see you're back at the starting point, cosine. So that means this is going to be the 5th derivative. This will be the 6th derivative. This will be the 7th derivative. This will be the 8th derivative. Okay? So every multiple of 4, you get back to the start. So like 48, 49, 50, 51, 52. 52 is a multiple of 4. I don't think I even knew that. But since every multiple of 4, the derivative, the multiple of 4, goes back to the start, the 52nd derivative of cosine, just cosine, okay? That's how you do it. You just like break it into 4s and see what's your remainder after that. So if I ask you for like the 81st, this would be the 80th derivative because it's a multiple of 4, 4 times 20. And this would be the 81st derivative, negative sign. Notation. Notation is important, guys. Pay attention to notation of like what you have. This is the first derivative. This we talked about meaning the third derivative. Comes from the fact that you start with dy dx. If you take the derivative using this notation of dy dx and you multiply the d and you multiply the dx, you'd say that's d squared y over dx times dx, which is dx quantity squared. Well, like we write it like that, though we know that it's this squared. But anyways, if you're taking a derivative of a derivative, this would be the notation of the second derivative. This would be the notation of the first derivative. You have of the third derivative, sorry. This is the notation of the third derivative. You have the first derivative, which means you need to take the derivative just 2 more times, not 3. Because you already have the first, taking the derivative will get you the second, taking the derivative of that will get you the third. Okay? So the second derivative would be our first derivative of this. I have a product, I have to use the product rule. Okay? Now, when I take the derivative of this, heads up, the 1, it's like gone, it's just sine x. The derivative of sine x is cos x. But now I have another product over here, and I have to use the product rule. Derivative of the first times the second plus the derivative of the second times the first. And easy simplification can be done here. I'm just rewriting this. I'm not taking the derivative again. I'm already done. I have a cos x plus a cos x. I have 2 cos x's. And then I have a negative sine x times x, so I have a minus x sine x. Okay. Again, notation, pay attention. This is the first derivative. I'm asked for the fourth derivative. If you take the derivative, you get the second derivative, 4x cubed minus 6x plus 0. The 2's gone. If you take that derivative, you get the third derivative, 12x squared minus 6. If you take that derivative, you'd then be left with the fourth derivative, 24x. Okay? Kept going, you'd eventually get to 0. Now, if you have anything else, like this, since this is a negative power, we're not going to eventually go to 0. We would just like keep subtracting 1 and get -2, -3, -4. So not always will like derivatives of derivatives eventually lend to 0 when we deal with powers. This is notation for the third derivative. I'm given the original function, so I have to just take the derivative 3 times. So I have 2x plus. I'm not using the quotient rule here. You could if you wanted to, but it's easy enough where I could just write it as x to the negative first and use the power rule. I'm not going to simplify this because I need to take the derivative of it, and I know like power rule only works in a numerator. And I have positive 2x to the negative third. If I take the third derivative, the derivative of 2 is gone, but this derivative is negative 6x to the negative fourth. Again, I'm subtracting 1, minus 1, not adding 1. So the third derivative is negative 6 over x to the fourth. Okay? And just remember, like, if you plugged in values into this, you get the slopes of this. If you get plug in values into that, you'd get the slopes of that. If you plug in values of that, you'd get the slopes of this. If you plug in values into this, you'd get the slopes of this. If you plugged in values to this, you would just get a y coordinate on that. Okay, like you would say it's the slopes of some other function that we can't even think about yet, but we will have to think about, called an antiderivative. Second semester. Right now, we're just like, all right, we start with f. F is where we start. All right, that leads us to table problems, where we're asked to get numerical answers, but we're not given functions. We're just given notations. Like k is g plus f. And what's k prime of pi? So like you will take the derivative of both sides, and the derivative of k is k prime. The derivative of g plus f is just g prime plus f prime. Like the derivative of a function is the tangent slopes of the function. So if you want k prime of pi, well, I'm just plugging in pi into g prime and f prime. G prime of pi, I use my table to get my values. -4. F prime of pi is -1. I get -5. That's what I'm looking for, some numerical answer coming from this notation and this table of information. If you have a constant times a function, the constant multiple rule still applies. You don't have to use the product rule here. You don't have to use the quotient rule here. You rewrite this as 1/4 times g. This stays as 3 times f. And the derivative of this is just 3f prime. The derivative of this is 1/4 g prime. You're asked to find these values at 2. So you have 3 times f prime of 2 plus 1/4 g prime of 2. F prime of 2 is -2, so I got 3 times -2. G prime of 2 is -1, so I have 1/4 times -1. That leads me to -6 plus -1/4. This is -24 quarters. plus negative a quarter, which is negative 25 quarters. Don't make mistakes plugging in and evaluating numbers. That should be the easy part, but it's where most students make mistakes. Now we have a constant times a function. And in this case, we have a product. There are two ways that I teach you to deal with this, okay? Two ways. One, I like to call baking in. You can bake in the 2 to the g of x, which means you could treat this as just a product of two things, 2g of x and f of x. We just talked about if you take the derivative of a constant times the function, the constant stays times the derivative of the function. So that's the derivative of the first times the second plus the derivative of the second times the first, 2g of x. Okay, so that's one way, baking in. The other way, which you may prefer, is what I call leaving the constant out. I love to leave constants out if we're using quotient rules. I think it makes things a lot easier to leave it out with quotient rules. With product rules, it may or may not help you. What do I mean by leaving out is leave the 2 out. It's just a constant. Worry about it later. And then treat this as a product of g and f. And you can see these two are the same. This, the 2 is baked in. It's already distributed in. This one, you would have to distribute maybe now or later. Whichever way you do it, I don't care. Just do it correctly. We're finding j prime of 2. Let's just do the work over here. I'm not going to show plugging into. I'm just going to get the values. G prime of 2 is negative 1. F of 2 is 4. This is multiplied. F prime of 2 is negative 2 times 2. G of 2 is 3. So I get negative 8 plus negative 12, which is negative 20. I get the same value here. It'd be negative 1 times 4, which is negative 4. And then negative 2 times 3, which is negative 6. I'd get negative 10, but then I'd multiply that by 2. Okay? This guy, nothing to bake in or leave out, but it is a product, so you have to use the product rule. Derivative of x is 1. Derivative of the first times the second, plus derivative of the second times the first. Plug in 3 for x. So this is g of 3. This is g prime of 3. But then it's times x, which is times 3 if you're plugging in 3. It's important to do that. G of 3 is 4. G prime is negative 2. Negative 6 plus 4, negative 2. Okay, quotient rule. No big deal. Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. We're plugging in 4 everywhere. I'm not going to show you me plugging in 4 everywhere. You guys probably aren't doing it anyways. G prime of 4 is negative 3. G of 4 is 2. F of 4 is 3. F prime is negative 4. Okay. I get negative 9 Don't you dare try to cancel that with this 9. You can only cancel over multiplication. This would be plus 8, so that's negative 1 over 9. Okay, you're not allowed to cancel numbers if you have addition in between. Don't try to do that. Doesn't work. Use numbers to show how that doesn't work. For example, this is always what I do to check, like, can I simplify like that? Let's say I have 2 plus 3 over 2. This is, let's make it easier. 2 plus 4 over 2. This is 6 over 2, which is 3. We know that, okay? Like 6 over 2. If you canceled the 2's and said, oh, that went away, then you would get an answer of 4. That's not right. So don't do that, okay? Use numbers to help you understand when you can simplify or not. Now, here is the example that I like to show of like, yo, leaving out is going to be better than baking in. You see that 2 there? Before taking a derivative, I know I could pull that 2, which is a constant, out and write it as 1/2 times, right? Because if I multiplied this 1/2 in, I would still get x squared over 2f of x. So with quotient rules, especially because you're going to be squaring the denominator, very advantageous for you to leave stuff out and worry about it later. Leaving the 1/2 out, taking the derivative of this quotient, using the quotient rule. Derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. Cursor's going to come back to f of x. Wait, I just made the mistake. The derivative of the bottom is just f of x. I mean, the bottom is just f of x. I've left out the 2. This 2 comes from the derivative of x squared, okay? Derivative of x squared, 2x. Derivative of the first times derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. The 1/2 is out. Plugging in 2, I get a 4 here, because I'm plugging in 2 for x. F of 2 and f prime of 2 is what I need. F of 2 is 4. F prime of 2 is negative 2. F of 2 is 4. F prime of 2 is negative 2. Don't cancel those 16s. 16 plus 8, 24 over 16. I can go ahead, since it's multiplication, and say this is 12 over 16. Divide or like factor out 4, and you get 3/4. Product rule. Plug in pi. G prime of pi. I'm going to write that down because cosine of pi is negative 1. Sine of pi is 0. Look at that. Our friend, the unit circle, comes back. Since the sine of pi is 0, 0 times whatever g of pi is going to be 0. I just need to have g prime of pi and then take the opposite of it. G prime of pi is negative 4. Take the opposite of it. I get 4. Bake in, leave out with product rules. I prefer to bake in. Quotient rules I like to leave out. The derivative of 3x squared 6x times the second plus the derivative of g is g prime times 3x squared. Plugging in 3, I get big old 18 times g of 3. I'll come back to that. Plus g prime of 3 times 27. This is going to be fun to do. G of 3, G prime of 3. Give me a 0. Give me a 0. G of 3 is 4. G prime of 3 is negative 2. G of 3 is 4. G prime of 3 is negative 2. All right, well, I know this is negative 54. That's easy. 18 times 4. Double 18 is 36. Double 36 is 72. Let's just check that. 2, 3. So, yeah. 72 minus 54. I'm almost 30 away, so I'm 28 away. If this was negative 52, you can double check by doing the math. Ooh, 18. I'm almost 20 away. 18. Not 30. 44 is like 30. So 52, 62, 72, that's 20. 2 less, 18. Okay. This is 6, this is 1, this is 8, this is 1, 18. Not too bad. Now, I might not give you a table and ask you to answer these table problems. I might give you some graphs. Now, what's different about these graphs than the graphs that we've been kind of like analyzing is that it's a bunch of like line segments. These are like piecewise functions of just lines. Or have F as the black line and G is the red line. If I ask you what's F of negative 3, negative 1, negative 2, negative 3, like you can find the Y value, that's 1. If I ask you to find F prime of negative 3, I'm asking you for the slope of F at negative 3. Well, since this is a line, we know the slopes are going to be the slopes of that line. The slope of that line is negative 1. G of negative 3 is going to be 2, because that's the Y coordinate of G at negative 3. G prime of negative 3 is going to be the slope of G at negative 3. And that's 0. And that's the idea behind like we are going to like create a table of information based on our graph's points and slopes, which we can find because it's just straight lines. At 1, F of 1 is negative 1, F prime of 1 is 0 because the slope here is 0. G of 1 is 1, 2, 3, 4. G prime of 1 is positive 1. F of 4, 1, 2, 3, 4 is 1, 2, 3. F prime of 4, I go up 2 over 1. You can use rise over run to find slopes, right? G of 4 is negative 1. G prime of 4 is down 1, 2, 3 over 1, negative 3. Okay? So I just kind of created a table of information. Now, quickly, if I asked you what's F prime of 2, this sharp point right here, there is no tangent slope at a sharp point. So you can't like get a slope at this sharp point. You will never be asked to answer one of these questions at a sharp point. If you are, the answer is going to be just like undefined. You know, like I don't have a slope there. So just like, cool. Ooh, this is a good one. 3 1/4. 3 1/4. What? I don't know what the points are. 3, 1, 2, 3 1/4. I don't know those points. But I don't need the points because M prime, again, don't use the quotient rule. This is 1/2 f of x. The derivative, keep the constant, take the derivative of the function, is that. Derivative of g is g prime. If I'm asking for M prime at 3.25, I just need the slope of f at 3.25. At 123.25, it's the slope of that is f. I'm going up 2 over 1. The slope of g at this point, that's the down 1, 2, 3 over 1. And I get that. Negative 2. Okay. More constants. Don't freak out. Figure it out. Leave the constant. Don't use the product rule. Constants are easy to deal with. Negative 2. F prime is -1, G prime is 0. G prime is 0, F prime is -1. So I have 2 times -1 minus 7 times 0, which is -2. Now we're into product rules and quotient rules because it's not a constant, it's functions times functions. So F prime G plus G prime F, plugging in 1. F prime of 1, G of 1, G prime of 1, F of F. Whoa. Derivative of the first times the second plus derivative of the second times the first, not the derivative of the first. Come on. I'm better than that. All right. I did this. G of 1 is 4, G prime of 1 is 1. F of 1 is -1, F prime of 1 is 0. So my answer is just -1. Another product. This is not a constant. This is an x or an f of x or some function. It's a function times another function. Use the product rule. Derivative of the first times the second plus the derivative of the second times the first. Derivative of x is just 1. It's just a line. -3. F of -3, F prime of -3 times -3, because I'm plugging in -3 for x. F of -3 is 1, F prime of -3 is -1. +3 plus 1, 4. F of -3 is 1, F prime is -1. All right, 4 more. Oh man, 3g of x, 2f of x. It's a quotient. Since it's a quotient, I'm going to leave out constants. If you wrote this as 3f's times g over f, this will be easier to do and then calculate. Because we can just leave out the 3/2, multiply by this derivative. Derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. At 1. -1, 0, 4, 1. -1, 0, 4, 1. Okay. Not bad. 3/2 times -1 minus 0 over 1. That's -3/2. It helps when some of these slopes are zeros when we're finding the values. Since it's just 2x, I can bake this in. If you want to leave out the 2, leave out the 2. I don't know, I've kind of been consistent with like, yo, leave things out. So why don't we leave out the 2? Derivative of the top times the bottom, minus the derivative of the bottom times the top, all over, bottom squared. G prime of 2, G of 2. Oh, there we go. Here we go. I'm glad I gave you one example like this. At 2, G prime of 2 does not exist. The slope at, no, but I'm not talking about 2. If I talked about 2, then this answer would be does not exist because G prime of 2 would be like undefined. But it's not, it's at 4. So G of 4 is -1, G prime of 4 is -3. So I have 2 times -1 minus 12 over 1. That's negative 13 times 2, which is negative 26. Okay, negative 1 minus 12 is negative 13. I like to add opposites so that I don't make mistakes with subtracting with positives and negatives. All right, last two. We just have a constant. Leave the constant alone. Take the derivative of the function. Oops. We have a product, though. X squared g of x. Just like no, this is a good example of like sometimes you got multiple things going on. Don't think it's like, oh, this is just a sum, so we're just taking the derivative of the left and the derivative of the right. It's like, oh, I'll take the derivative of the left piece. But the derivative of the right piece is a product. I have to use the product rule. Okay, so just like heads up there. If I'm plugging in 1, I need f prime of 1. 2, I need g of 1. I need g prime of 1. F prime of 1, g of 1, g prime of 1. F prime of 1, 0, 4, 1. So I got 0 plus 8 plus 1. I get 9. Last one. It's a product. It's a messy product, but it is a product. It's x times this. I'm going to just use the product rule. You can think about distributing, but then I'd have like a product and then a non-product. It's like you're going to have to use the product rule. So the first times the second. That's that entire second. Plus the derivative of the second. 2f of x's derivative is 2f prime of x. I don't have to use the product rule there. The derivative of 3 is 0. So like that 3 goes away when you're taking the derivative of the second piece, and then times the first. And we're talking about negative 1. So I have 2f of negative 1 minus 3 plus 2f prime of negative 1 times negative 1. All right, so f of negative 1 is what I need, and then I'm subtracting 3, not multiplying by negative 3. Be careful with that. F of negative 1 and f prime of negative 1. All right, good. I gave you one of these. Negative 1. I gave you one of these. Negative 1. Now, this usually never happens on your quiz. It's not going to happen. There's a sharp point at negative 1. There's no slope of f at negative 1. So since there's no slope of f at negative 1, that's undefined, which means your answer is undefined. You typically don't see this for like my quizzes or my tests, but on the AP tests, like sometimes they throw that at you. So, just keep it in mind. But for your quiz, like I'm going to be picking points that aren't going to be sharp points so that we do get numerical answers and you can't just like guess undefined. And undefined is going to be the answer, okay? This is like good practice of do you know your derivative rules? We got some other trig functions in here. Secant, cosecant, tangent, cotangent. That's lesson 4. One more lesson to go after this. Later.